Now let us look into some of the basic operations on signals. The basic operations can be on the signals can be done on the independent variable or on dependent variable. So consider a signal y of t is equal to x of t, or sorry, consider a signal x of t and signal x of n. In case of case 1, when the operations are done on independent variable, they are done on either t or on n. In case they are done on dependent variable, they are done on the value of x directly. Now first we will look into the basic operations that are done on the dependent variable. One of the the first one is amplitude scaling, which can be written as y of t is equal to c into x of t, or y of n is equal to c into x of n. So in this case, the signal y of t is obtained by scaling x of t, and the same explanation can be given for y of n also. The second one is addition, which can be represented as y of t is equal to x1 of t plus x2 of t. Here the signal y of t is obtained by adding the signals x1 and x2. Similarly, y of n is equal to x1 of n plus x2 of n. Similarly, other basic operation on the dependent variable can be multiplication of the signals, so which can be represented as y of t is equal to x1 of t multiplied by x2 of t, or y of n is equal to x1 of n multiplied by x2 of n. The next one is differentiation. In this case, y of t is equal to d by dt of x of t. Here the differentiation is done on the dependent variable x, or y of n is equal to x of n minus x of n minus 1. The fifth basic operation is integration, which can be written as y of t is equal to integral t1 to t2 x of t dt, or y of n is equal to sigma n equal to capital N1 to N2 x of n. So in case of discrete signals, the integration can equivalently be represented as summation. So these are some of the basic operations that can be done on the dependent variable. Now we will look into some of the basic operations that can be done on independent variable. The first one is time scaling, which can be written as y of t is equal to x of at. So if a is greater than 1, y of t is obtained by compressing x of t. If a is less than 1, y of t is obtained by expanding x of t. So for example, let us take x of t, which is as shown in the figure. So here x of t is in the range of minus 1 to 1, and it has a value of maximum value of 1. Now if we try to plot x of 2t, we know that x of 2t is a compressed version of x of t, so it would be as shown in the figure. Here also the maximum value is 1, but x of 2t is present in the range of minus half and plus half. Similarly, x of t by 2 can be drawn as shown. Here x of t by 2 will be an expanded version of x of t. Here it is present in the range of minus 2 to plus 2. So this is for the continuous time signal. Now let us take the example of a discrete time signal which has the values at the instant 0 and 2 as 2 and 1. It means that y of 0 is equal to 1, sorry, 2, and y of 2 is equal to 1. In this case, we can write y of 2n as compressed version of x of n, which will, sorry, y of 2n as compressed version of y of n, which will have the values 2 and 1 at the instants 0 and 1. Similarly, we can write y of n by 2 as shown. In this case, the values 2 and 1 are present at the instants 0 and 4. At all the remaining instants, the values are 0. So, given a signal x of t or y of n, we can obtain its compressed or expanded versions by substitution, and we have explained the same by the examples here. Another basic operation that is possible on the independent variable is time delaying or advancing on the independent variable. Let us consider a signal x of t, then x of t minus t naught is time delayed or advanced version of x of t. It would be a time delayed version if t naught is greater than 0, and it would be an advanced version if t naught is less than 0. So let us consider the signal that is shown in the figure, which is x of t. Here the signal x of t is present in the range of 0 to 2 seconds. Now if we try to plot x of t minus 1, which is delayed version of x of t, it looks as shown in the figure. In this case, the signal is present in the range of 1 to 3 seconds. So we see that from x of t minus 1 is obtained by delaying. Similarly, from x of t plus 1, which is advanced version, can be drawn as shown. In this case, x of t plus 1 is present from minus 1 to 1. So here we see that x of t plus 1 is obtained from x of t by advancing x of t by 1 second. Now let us consider another example for the same case, which is where x of n is equal to 1, 2, 3, 4. Here the value of 1 corresponds to n equal to 0. So now from this, if we try to find out x of n minus 2, which is delayed version of x of n. So in this case, x of n minus 2 is obtained from x of n by delaying by 2 samples. So here the values that we get would be 0, 0, 1, 2, 3, 4. So the value of n equal to 0, sorry, the value of first 0 corresponds to the instant n equal to 0. Similarly, the signal x of n plus 3 can be written as 1, 2, 3, 4, 0 and 0 and so on. Say. In this case, the value of 4 corresponds to the instant n equal to 0. Here x of n plus 3 is obtained from x of n by advancing x of n by 3 samples. Now let us look into another case of a basic operation on an independent variable, that is reflection or transposing of independent variable, which is time. So to explain this, Let us consider a signal x of t, which is as shown. In this case, the reflection corresponds to x of minus t. So in case of reflection or transposing, x of minus t can be obtained from x of t by reflecting the signal around t equal to 0. So the reflected or transposed version of x of minus t can be obtained as shown. Similarly, consider another signal x of n, which can be written as 0, 1, 2, 3. Here 2 corresponds to the instant 0. From this, x of minus can be written as 3, comma 2, comma 1, comma 0. Here the signal x of minus n is obtained by reflecting the signal around the value which corresponds to n equal to 0. Now let us look into another basic rule of time shifting and scaling. For this, let us consider a signal x of t, and there is a derived signal from this, which is y of t is equal to x of at minus b. So in this case, y of t is obtained from x of t by delaying x of t by delay x of t by b samples, then time scale by a. So similarly, from x of n, say y of n is equal to x of an plus b can be obtained by delaying x of n by minus b samples, means this is advancing x of n by minus b, then time scale by a. Also please note that this delaying x of t in the y of t is equal to x of at minus b is by b second. So this is general rule of thumb that needs to be remembered whenever there is a derived version of a signal x of t, which can be written as x of at minus b. Now let us look into some of the problems related to basic operations on independent and dependent variables. Suppose there is a signal x of t and its derived version y of t, which can be written as x of t minus 2 by 3. You have to find out how y of t is obtained from x of t. We know that if there is any signal y of t which is a derived version of x of t as x of at minus b, y of t is obtained from x of t by delaying x of t by b seconds and time scaling by a. So from this we can say that the given y of t can be written as x of t by 3 minus 2 by 3. From this, y of t can be obtained from x of t by delaying by 2 by 3 seconds and then time scale by 3, or rather say 1 by 3. So by doing these operations, y of t can be obtained from given x of t. Now let us consider another signal x of t, and there is a derived version of x of t as y of t is equal to x of 2t plus 3. It's given that x of t is not equal to 0 for 0 to capital T. So you have to find the region, or you have to find the region in which y of t is not equal to 0. So we know that x of t is not equal to 0 for 0 less than or equal to t less than or equal to t. From this, x of 2t plus 3 is not equal to 0 for 0 less than or equal to t less than or 2t plus 3 less than or equal to t. That implies minus 3 by 2 less than or equal to t less than or equal to t minus 3 by 2. So the obtained range is the one for which y of t is not equal to 0. Now let us consider another problem where there is a signal x of n and there is a derived version of x of n which is given as y of n is equal to x of 2 minus 3n. We have to find out how y of n is obtained from x of n. So we have to find how y of n is derived. So in this case it's given that y of n is equal to x of minus 3n plus 2. So y of n is obtained from x of n by advancing x of n by two samples, then time scale the obtained signal by 3, then transpose the resultant signal around 0. So by performing these operations, we can get the required y of n from x of n. Now let us look into the elementary signals which are mainly used as building blocks for the construction of the complex signals. The first elementary signals we will be looking into is impulse function. So we'll look into both continuous time and its discrete time equivalent. So the continuous time equivalent is represented as delta of t and the discrete time equivalent is represented delta of n. So delta of t would be equal to 0 for t not equal to 0 and also integral minus infinity to plus infinity delta of t is equal to 1 and in case of delta n it is equal to 1 for n equal to 0 and it is 0 else. Some of the properties of the impulse function are integral minus infinity to plus infinity delta of t minus t naught multiplied by x of t is equal to x of t naught. This is the case because delta of t minus t naught is equal to 0 for t not equal to t naught. So at t equal to t naught, the integration evaluates to x of t naught. Similarly, sigma k equal to minus infinity to plus infinity, x of k multiplied by delta of n minus k is equal to x of n. Now another elementary signal that we would be looking into is unit step function. For continuous time case, the unit step function is denoted as u of t. For discrete time case, the same is denoted as u of n. U of t is equal to 1 for t greater than or equal to 0. It's 0 otherwise. Similarly, u of n equal to 1 for n greater than or equal to 0. It's 0 otherwise. When u of t is plotted, it looks as shown. So for t greater than or equal to 0, its value is 1, otherwise it is 0. Similarly, for t n greater than or equal to 0, u of n is 1, otherwise it is 0. Also, u of t can be written as integral minus infinity to tau delta of tau d tau. Similarly, u of n can be written as equivalently by a summation which is sigma k equal to minus infinity to n delta of k. Also, please note that delta of n can be written as u of n minus 1. Another elementary signal that we would be looking into is ramp function. In case of a continuous time case, ramp function can be written as r of t is equal to t into u of t, which means it would be t for t greater than or equal to 0 and 0 otherwise. Similarly, r of in discrete time case, r of n can be written as n for n greater than or equal to 0 and it is 0 otherwise. So this can be written as n into u of n. So when plotted, the ramp function in continuous time case looks as shown. It would be 0 for t less than or equal to 0 and for t greater than or equal to 0 it is t. Similarly, r of n when plotted, for n less than or equal to 0 it is 0. For n greater than or equal to 0 it is um, n itself. Now another elementary signal that we would be looking into is exponential signal. In case of continuous time case, exponential signal can be written as x of t is equal to b into e power at. If a is greater than 0, it's a rising exponential. If a is less than 0, it's a falling exponential. Um, and similarly, discrete time exponential signal can be written as x of n is equal to b into r power n. Now, the last category that we would be looking into is sinusoidal signal. In case of continuous time, the sinusoidal signal can be written as f of t is equal to a into cos of omega t plus pi. And in case of discrete time case, the same can be written as x of n is equal to a into cos of omega n plus phi. The continuous time signal is periodic with a period of 2 pi by omega, and the discrete time signal is periodic um, if and only if there exists n such that omega n is equal to 2 pi k, where k belongs to z. So by default, a into cos omega n plus phi is not periodic. For it to be periodic, it must there must exist a n and k such that k belongs to z and n belongs to z and omega n is equal to 2 pi